today, in the few minutes which we have together, we are going to discuss about what is actually one of the most fascinating concepts of physics, namely that of waves. Waves are so interesting because they occur in so many different disciplines. You could think, for instance, about water waves, waves you see in the sea, or sound. My voice is doing is to vibrate the molecules to alter the local pressure to propagate sound, or light, optics, which is also a wave in the electromagnetic field. There are gravitational waves, for instance, and you might have heard about things like wave mechanics, which is more famously known nowadays as quantum mechanics. So lots of different things to consider when we speak about waves. To take a concrete example, and something which is familiar, let's consider the scenario of a kid who throws a stone in a pond. We all did that ourselves, so of course we're familiar with what happens, but we see something like this, a function for distance, x, from which we are looking at the disturbance on the water surface. We would see that there are regions where there is a surplus of water and over to compensate where there is a depletion of water. And this is one snapshot of the phenomenon. If we would let time evolve, if we would make a movie, we would see that this thing would actually propagate like this in time. So a wave is precisely something that connects space and time. And how do we connect space and time? Actually, you might have heard about this joke of the customer in the restaurant who doesn't want to pay the bill because as the waiter is making the total, he's adding the beer, the fish and chips, the cigarettes, and the customer rightly complains that how can you add these things which have nothing at all to do, which have nothing in common. It's the same in physics, right? You cannot add a meter to a second. Doesn't make sense. The solution in both cases is, of course, to convert the quantities into things that are compatible. So in the restaurant, we actually attach a price to each item, and then we can add the price. Or in physics, we can do the following thing. We can divide this quantity, we can divide time by another time, and then it becomes a number. And we do the same with the distance. We divide it by another distance, and then we've got two numbers which don't have any dimension. They are dimensionless quantities, and then they can be combined. How to choose these things? Well, for the time, a natural thing for the wave would be to measure the time it takes for the wave to complete its cycle, to go up and down one time. This quantity of time we call the period of the wave. And for the distance, it's even more easily seen because I can plot it on my sketch like this. This is the extent, the size of the wave in space. How much distance it requires to complete its cycle in space. And this is the counterpart, which we call the wavelength. Now we can combine them, and actually instead of adding them, I am going to subtract them. Like this we can satisfy our Western obsession that as time progresses forward, then things go from left to right. This is a convention, right? Otherwise it could be a plus. More importantly, what is the shape of this oscillation, this wiggling that I put there? You are surely familiar with that as well. This is something that corresponds to projection of a rotation on the axis of a circle. Yeah? So if you consider something that goes round like this on the circle, and you look at the shadow we would make if I project it on the y-axis, for instance, it go up and down, and then if I let my pen drift, you see that indeed it reproduces this up and down motion corresponds to this wave that I've sketched above. This is actually the sine function that we have in the circle. If we do the same thing on the x-axis this time, so going left and right, and letting the pen drift, then we have the counterpart oscillation like this, which we call a cosine. These are the two important trigonometric functions in the circle. So that's the way for us of physicists is the cosine of this argument that connects space and time through this wave vector and this period. Actually, because we like to make things even simpler, we wouldn't use the fractions. We would do something which is even simpler than that, which consists in multiplying rather than dividing. And this is a cheap trick. We just define quantity that are the inverse. So the wave vector is defined as the inverse of the wavelength. And similarly, the frequency is defined as the inverse of the period. Like this, I've got a product, nice product, and the minus to connect space and time as we go from this left to right progression. And as we've got a nice mathematical formalization of the problem, we can look at the physics of it, which means what are the kind of phenomena that arise when things happen. Let's consider, for instance, this likely scenario where we bring another character into the story, like a little girl, that I would put on the right, and maybe this little girl well, very likely, if the boy is throwing a stone, she'll do something similar and she will propagate her own wave. And then the question becomes, what happens when the wave of the boy meets the wave of the girl in the pond? We all want to know these kind of things, right? And this describes the phenomenon which we call wave interferences, yeah? Which is the addition of waves. And it's very simple, really, even though it could be a bit counterintuitive, but you're surely all familiar with the type of things that happens in this case. Consider that there is the maximum of the wave from the girl and the maximum of the wave from the boy. When this meets, there is double the amount of wave, of course. The same for the depletion. If there is less water from one wave and less water from the other wave, when these things meet in space-time, we will get even less water. Maybe we'll remove completely the water and see the ground of the pond, things like this. This is called constructive interference, where the two waves reinforce each other's behavior because they are in phase, they are doing the same thing. On the opposite, we could have destructive interference, and this is more interesting because this is counterintuitive. But it is equally simple. What happens is that the surplus of water, let's say from the girl, is met by depletion of water from the boy. And then there is compensation. More water and less water gives back the average. This is counterintuitive because although we have the two waves, at their meeting point, it's as if there would be no waves at all. They cancel. That's the destructive interference. If there would be a duck in the pond at this point, you wouldn't notice that there are kids throwing stones because the water wouldn't slosh back and forth. So you see that the algebra of waves is more interesting because it's different from the algebra with which we are used to work, which is 1 plus 1 equals 2. With wave, we've got things like 1 plus 1 equals 4, that's constructive interferences, or 1 plus 1 equals 0, destructive interferences. And to make this algebra even more accurate, more precise, we could look at what happens with our mathematical description in terms of our trigonometric function. The problem is that the sine and cosine, they're actually nasty functions, right? Because they'll go up and down, they accelerate, slow down, they even stop, change direction. It's a messy function. It's a difficult function to work with. It's much simpler to work on the circle because there you've got uniform motion along the circle. So actually, instead of working with the sine or cosine independently, we prefer to work with what is known as a complex number. And granted, the name is a very bad one because it looks like it's complicated, right? It's much better to call them like wave number, for instance, because it's precisely what they are. This number, they describe wave. But what are they? They are waves they are numbers that connects the x projection, that's the cosine, with the y projection, that's the sine. But to make the connection not simply an addition of two numbers, we add this new element which we call an imaginary number. The only thing you need to know about this number, if you have never seen it before, don't worry because this number is so important we tell you everything you have to know about it at university. Everything you need to know about it, actually I can write it there, is that its square is equal to -1. And as this is something counterintuitive, that a square number could be negative, well, the Italian people who invented that or realized that in the Renaissance, they called it imaginary number. The point is, which is also something that we explained to you, that we demonstrate at university, is that this combination of the cosine and the sine, the x and y projection of the trigonometric function in the circle, they behave like exponent, which means taking a power of a number. The power of which number we take is e, this Euler number, which is another constant, like you know pi, which is 314, well, e is another such number, which is something like 271. The point is that it's much easier to work with exponents, with exponential, than with trigonometric function. The algebra is much simpler. For instance, you've got these sort of things that the product of two exponential becomes a sum. You see that here we've got multiplication that becomes an addition. That makes working with wave easy because let's consider indeed the scenario where we superimpose, we make the interference of the wave from the little boy, which connects space and time in this way, and we add it, we superimpose it with the wave of the little girl, which is the same wave, and this we can justify on physical grounds because it's same pond, same water. We might assume that they flow type of same rocks, the same weight, and it will produce the same kind of wave. The only difference is that the little girls come with a minus here because she's propagating in the other direction. So now to see what happens when we interfere these two waves, we can use this sort of algebra which is above, which we break our exponential in this way. Don't forget that the I happens in these two places because it has to distribute. That's the way that additions and product work in parentheses. And if I do the same with the wave of the little girl, I break it into parts, you will notice that this part here is common to the both expression. It's the same term. And when a term is in common, what we like to do is to factorize it, to collect it, so that we can focus on what is different. And what is different is the sign that comes from the wave propagating in the opposite direction. Now let's come back at the mathematical level. If you remember that our complex exponential for the angle theta is the things that bring together the x projection, which is the cosine, with the y projection, which is the sine, you can very clearly see that if I consider the exponential for the negative angle, the one that goes in the other direction, that's minus theta here, then we have the same x projection, the same cosine here, so that's cosine again, but we've got the opposite, the reverse sign for the y projection. Therefore, I've got a minus there. And if I add these two things, you see that I cancel this part because they are the negative sign, while I reinforce, I double this part. Therefore, as a conclusion, if we come back to our wave, we've got twice the cosine of kx, and then here I would write the exponential of I omega t, but because we are describing ultimately the amount of water which is being displaced, we can come back to the real domain. The real domain of a complex exponential is the cosine again, so that gives me the cos omega t. So that's the important result here. It tells us the mathematical expression for the superposition of two waves with the same but opposite wave vector, same magnitude but going in opposite direction. And now we can leave the math apart because we are not mathematicians, we are physicists, so we are interested in what it tells us about the phenomenon itself. We make the interpretation of the formula. And what it tells us is something really interesting. It tells us that while space and time were initially connected like this, we had stitched space and time through some propagation, when the two waves go against each other, what happens is that the space and time disconnect. We have a factorization, which means that we've got the oscillation in space that becomes independent of the oscillation in time. The oscillation in time happens independently, so it will just go from this initial pattern of the boy wave, or this pattern from the girl wave, into something, their meeting point, the interference will correspond to a so-called standing wave, which means that we don't have propagation anymore. There is still oscillation, but it stays stuck in place. So that's an interesting phenomenon, which you are invited to check by yourself, because that's what we do as physicists. Once we made a theoretical prediction, we go outside in the real world and we throw stone at stuff to see if that works as is predicted by the theory. And we try to find the best platform to do that. So typically that wouldn't be with water. There is a simpler thing in this case to exhibit the phenomenon of standing wave, is to take a string, you pin one end on the wall, and then you make it oscillate like this on the other side. So you are going to propagate your wave, and as it will reach the wall, it will reflect back, the wall will reflect the wave, and if you keep yourself, if you carry on the oscillation as the wall is sending it back, then you have this scenario of the boy and girl throwing stone at each other, where you are propagating one wave and the wall is propagating it back. And this superposition, this interference, as we have seen, will produce a standing wave. And of course, your intuition tells you that is what will happen. If your intuition tells you otherwise, by all means, please make the experiment. We have very little time, so I will leave it at that. At university, actually, we don't do this in 10 minutes. We did this over weeks, months, over years, actually. We constantly look at such phenomena. But there is one thing I want to tell you, because it's so connected even to the kind of observation you can make if you throw a stone in the pond, which is this phenomenon also of adding wave, this time in the same direction, but with slightly varying frequency and wave vector. If you do that, and you can do the math, now you're actually equipped with the formalism to do the math yourself, you would see that what happens is this interesting phenomena of new waves emerging out of the waves that propagate like this, the one that you make interfere. This is the phenomenon of group velocity, a wave packet, a packet of waves that give rise to new types of wave emerging in the system. And in the pond, you can see that very interesting phenomenon where the body of fluid, the mass of fluid that actually propagate, goes at half the speed than the underlying wave that propagate as sine waves. It's very beautiful and counterintuitive thing to see. You are invited again to go in some place where there is water and to throw stuff and to see how the two types of waves do emerge. There are even more interesting things if you consider other cases. You could even have some sort of counterintuitive moonwalk effect where the body of the fluid is moving actually in the opposite direction as the waves themselves. It's kind of some optical illusion with waves. There are so many more things that we could discuss again, but of course we are not going to do this in this very short video, which purpose is to entice you, to give you a taste of what physics is about. It's something where I use math as a tool to describe the real world. And then if you're interested, if you think you've got the curiosity and technical skill to get into this, then we strongly invite you to not throw the stone into the water of the pond, but to actually throw yourself, to immerse yourself into this gigantic ocean of knowledge and wonders that is waiting for you to make the big dive.